Um, yeah, I kind of realized there's one small thing that was not working, but it's almost working. But we're gonna fix this today by just basically getting to implement the from and to wave function. Yeah, yeah. I think what's not correct is the amplitude of these edges, or is it? I'm not so sure it's correct. It's definitely not correct because of if we multiply this by these, let's do the following. I think it should be one, but I think that just basically means that in the last step of simplifying. So I almost forgot how it's been 4 days, 4 days, and I already forgot how I did it. Um, this is the yeah. So that's the last version. Why do I have this here still? I think that's all. That's not a bug anymore. It's not a bug anymore. Create edges, simplify, simplify recursive. That's where I wanted to go. Okay, so I'm still missing the case of what if the NBD equals 0? So simplify the edge amplitudes. Okay, so if nothing changed, no, if they're all the same, then I don't know what to do. But we'll explore these cases, right? I think for me to, I think we gotta get into now. Yeah, this is another to do as well. So we gotta get into. Let's just try to work on state vector, the state vector, self state vector. Exactly. And from state vector, I'm thinking whether I cannot just have the hypergraph. I think, yeah, I think we can just here define state vector as in like an empty list, right? And basically, I'm gonna assume qubits is correct, and then I'll just basically here say, if let's say vector is bigger than 0, then I think then what I should do is the same like I do with applied 2 qubit gates, right? Where I say yeah. So I have the state vector here. Yeah, exactly. So I think it's actually these. But this is hard coded for 2 qubits, right? And so I need to actually uh, to do this only supports Oh, yeah, but that's fine. It's 2 cubic gate. That's actually fine. But it's still, yeah, that's still another big to do here. Cool. So let's keep it to 2 qubits for now. So what do we do? So we do. So this is state vector. I think I should call it SV because it's just too. It's easy to make a mistake in here. State vector. State vector. So if the probability is non-zero, like I don't know why. Oh, I even do it like this, but if the probability is bigger than 0, then could hyperedge with, just okay. So what amplitude do I give it? I think none, right? Because, or just 1. I think this is gonna definitely have 1. Is it? No, new SV, right? Of course, this is what it has. It's just not new SV, sorry, but it's so the actual thing that's that's the. Oh wait, yeah, that's correct, right? So I basically pretend they're entangled, right? And then I just simplify it. Yeah, yeah, of course. I pretend that, zero is connected to zero, is connected to one is connected to zero, one is connected to one. So I pretend that they're entangled, and then I just let the entanglement simplify. And then create nodes. Okay, so add the nodes to the graph, add the nodes to the edge, and then at the end, after this, I should then do the simplification, right? Oh, come on. Simplify. Why am I using caps lock? Jesus. Simplify. Now the simplify. What did I need to give it? Simplify recursive. So simplify. I create edges. Blah blah blah. Okay, just like that. I love it. I love it. Yeah, it's still hard coded for 2 qubits, right? So it's not a problem. But so we just. I keep saying that. I have to come back, check the setup of OBS because I think that's slowing things down. Anyway, we self-simplify, people. And I am going to assume that we have 2 qubits. They're called Q0 and Q1. This is hard-coded. I will change that, okay? I mean, we can test that already. I think that would be. So I can just initialize it with basically, yeah. with an array of complex numbers. So which can have basically 4, right? Because it's yeah. So this is the type of array that we want. Have I done two-state vector? Turn on. So okay, so this is a whole new thing now. So I'm gonna keep that aside for now. So let's just not draw stuff. Let's not simplify stuff. It's just that's what we have. So what if I say yeah, well, just system equals hypergraph of 2 qubits, and I'm gonna give it a state vector, which I'm gonna define here by saying, what the hell am I doing? By saying that SV is equal to an array or a list of all arrays. So what if I initialize everything to 0? That's this. So what do we expect to happen? Expect to basically so expect to basically draw a first not to break. That would be awesome. The truth table. Since 1 is not a problem. Since 1 is not a problem. So I'm getting the element, the real part, plus the imaginary part. And so why is that a problem? I mean, so print prop. Maybe there's something wrong there that I didn't realize. Okay. This is a complex number. What's wrong with this? Truth value of an array with more than one element is ambiguous. So it printed this. Why did it print this? It's wrong. So it should do these plus these. These are two real numbers. I mean, what? What's wrong? Am I doing something with the I here? So what's print I, print svi, print this. I yeah, so okay, what what am I printing? Man, that's so stupid. I feel so retarded. Print I 0. So as vi is basically that, which is, yeah, the one component, the 0 component is 1, the 1 component is 0. And now I do svi.real. How do I do it here? Why does it here? Why does it work here and it does not work there? So that's I. That's SVI. That's SVI real. And that's SVI real. Like the real component cannot be. SVI real. Why? Why? I don't get that. Moment. What am I doing here? Oh. No, okay, wait a second. So this is what am I doing? So what is the excited state? Yeah, it's correct. The 0 component and the 1 component. And each of them are complex numbers. So I have 2 complex numbers. Okay, yeah, okay, so yeah, but then I'm stupid. Why does it even work there? So this is the 0 component. No, This is basic. So I want to check whether they're both not zero, right? Why does this even work here? Why does this even work here? Apply the gate. To the state vector. And each element is a complex number. So each entry is a complex number. Is it? Each is a complex number. Yeah, each is a complex number, exactly. Yeah, and I'm doing, I know, I'm doing this wrong. Each of these elements is a complex number. That's the problem. It's here. It's here, not here. That is correct. So the way that I had this here is that's correct. That's correct. That is correct. The issue is here. It's a complex number, what we're trying to get. Okay, but it has to be a valid, it's got to be a valid, I know. That's the way. That's the way to do this. I'm so dumb. I'm just so dumb. Okay, I'm just, I'm just so dumb. I'm just so dumb. So this is the state 0, 0. A is not defined. Oh, there you go. A is not defined. So where is A? And why is it not defined? Because I copy pasted it, obviously. Create the nodes. Where's A here coming from? The A nodes and the B nodes. Oh, these are the parameters. Qubit 0, qubit 1. Yeah. So these are here just actually given by us, hard-coded. Oh, come on. Oh, yeah. Well, now that doesn't work, definitely. Okay, now yes, please, please. Oh, come on. To unpack. Huh? Interesting. Okay, so that's the case where I just gave it like a 0, 0, so that already failed. Because I got one thing, not two. So let's take a look at simplify recursive. So, and I think that's how we're gonna really catch bugs, to be honest. So, okay, yeah, because here I return M if it's just like that. If the key's in M. are just 1. So what I need to do is I need to return m-amps. Yeah, that was the reason. Good catch. That's definitely wrong. That's definitely wrong. That's definitely wrong. Okay, the edge is duplicated. So this is a problem of the create edges, or create, I think so. So once I call simplify, I delete the edges and I create the edges. Oh no, because I print msimp. No, this is msimp. Yeah, but I somewhat have two edges, that's the problem. Right? Delete that. Go to create edges. So print amp. So if the keys are just 1, then for each edge in a M and for each Q in a ME, create a node Q and add it to the nodes. Yeah. That's it. That's all it does. So why is it going through? Why is it creating so many edges? Am I in this case? I should be in this case. Yeah, I'm in this case. But why does it create two? Oh, I think I'm stupid. I think this is because of the initialization here, isn't it? Yeah, of course, because I initialize the qubits regardless. Okay, so this is really a big else. Else we do this. Okay. So that still has the potential. I'm gonna keep the print here because it's useful. Creating edges. Creating edges, and I'm gonna remove these. Okay. Okay, that's cool. 0, 0. What if we do this? 1, 1. Oh, yeah, 1, 0. No, it makes sense. 0, 1. Okay, cool. 0, 1. Yeah, these are stupid tests. Okay, so this should be 1, 0. Yeah, and you know, and like these, I think we can build some tests to make sure I don't break stuff in a stupid way, right? Because it should be the 1, 1. Cool. What if I so we should also test for like things like that. QB1 is not entangled. Or even non-normalized stuff. Wait. Did it actually, what did it do? It actually built it. It actually did it. Did it normalize? That the thing just normalizes. Look at this. So the qubit 0 is in the 0 state, because this is 0. Remember this. This is. Maybe I should. Maybe I should, you know, do it like this, right? because that's I think I can do that in Python. Can I? I think I can do that in Python. Anyway, so maybe I can just do it like this, right? So this would be like this. Okay, cool. And so, oh, maybe let's do the let's work on the other one. Maybe just let's do the full trip, the full round trip, right? So from hypergraph to state. But yeah, I mean that actually has write it the correct way, right? Because cubed one is in the plus state. If what you give is like this, right? The thing is we've given it not normalized, and it seems like it's just normalized it, but I don't know why. Yeah, because it doesn't care about the amplitudes. I guess it normalizes them, right? If I give it all once, it should give me the plus state. There you go, plus state. Awesome. Now, what if I give it the? So what is the minus? So what is that? What is leading to the minus state? To the, I'll say 0 minus, right? So 0 minus. What am I doing? Plus minus. Okay, so you have 1 minus 1 minus 1, 1. So in theory, that's this. And that should be, oh, okay, something's wrong here though. Okay, so here it doesn't work, and it doesn't work. Well, it doesn't work. It does work. It just does something really weird. No, it works actually. One is a plus, one is a minus. It's just it doesn't process this the way that I expected it to do, and that's what I'm saying. These, okay. So if you have, yeah. So if I have edges out just one node, like those edges don't make sense anymore either, right? And I think that's what I'm missing here. No, but there's something wrong here because the edge I see, they contained values for the 2 qubits, and this is definitely wrong. So Q0 is 1 here, and here's this thing. These values are definitely correct. No, it's definitely not correct because they're both for Q1. So that doesn't make any sense either. Okay, but this way, so this is definitely to test. Although to be honest, to be fair, this was supposed to be this way. But I don't know. I mean, I think that shouldn't be the reason. Yeah, that's wrong. That's definitely wrong. Okay, cool. But at least we can now initialize hypergraph given a something like that, and then we can test this out as well. So let's go back to the easy cases, because now I want to basically implement the yeah. So there's some edge cases that I still need to polish, but now let's implement the two. Yeah, well, I have basically implemented it already, in a sense. It's also in the apply 2-qubit gates, because what I do is I calculate the local 2-qubit state, right? So I go through, I just multiply the nodes. Yeah, but I think that's wrong, isn't it? So I think I can just totally reuse this part. Yeah. It gets all the nodes from qubit 1, all the nodes from qubit B, qubit 0, qubit 1. And what it does is, it does, oh, this seems complicated. I can't believe I coded this. So A, B, and then uh, if they exist, and if they belong to the same edge, which is non. Oh, that's another bug. That's definitely another bug, because could be one qubit is entangled and the other not, so they don't share an edge. Okay, that is definitely a bad bug. But I can basically, for now, I can repurpose this with the bug included, and then I get what I want, right? I should probably turn these into functions and reuse them properly. But yeah, basically, to state vector is no, you just give it a you know what would be cool? It would be cool if to state vector allows you to get sort of the partial trace of that, or to get like a you know, you just give it a list of qubits. I think that's what would be cool. Hard coded for 2 qubits at the moment. So what you know, what it would do is it would just take the qubits and then just do that, and then return USB. So so like if new USB is not none, return it, else something went wrong. And I don't know what. Cool. So I should actually print that and return a, no, that's basically, I'll do an empty array. Exactly. And so we just return that, and so yeah. So we just print the error, but return that anyway, right? Which is just maybe an empty array or whatever here. is none. Okay, to state vector. So if now I go here and I don't want to draw it, but what I want to do is print system to state vector, and I just give it basically q0, q1, right? And that should work, and it doesn't. Name gate is not defined. Idiot. I'm such an idiot. What gate? I don't want to apply any gate. I just return SV. That's it. State vector. I don't apply any gate. Why is my laptop so slow? I say the same in every video. Awesome. Yeah, there you go. We get back the same thing. It would be cool to return an actual latex thing, but for now that's okay. I'm curious if I do these. Yeah, it returns it properly normalized. Okay, cool. Yeah, but we know that it doesn't work. Yeah. Okay. Okay, so we're done with these, but it doesn't work at least. But we can now kind of test, right? So we can start thinking about building tests and say, you know, I give it this, I give it this state vector. I have this circuit, and I expect this state vector. And with this, we can, you know, at least define some tests to make sure that when we play with these, we don't break anything essential, basically. But I think I'm going to leave it here today. It's been a bit busy lately with other stuff, so it's just a small one. But at least we've got these ones implemented, and now like for one, the code is super ugly, but it's still far from done. I thought I was really optimistic, I think. First of all, it does that. I think it doesn't even like. I wanna simplify. I wanna fix. Make sure the simplify works, right? Because we basically, I just basically show you that it doesn't work. If I give it this, right? I want this to be so. So I can give it this, right? So that's this thing. It is format. Yeah, but it obviously doesn't work because it does. Wait, what? I thought it didn't. What is it that what is it that I tried that it didn't? Isn't it these? They're both in the plus state. And if I minus these two in the middle, oh, that's when things don't work. When you add, okay, things don't work when you add like these nasty phases because it's when initialized is not initialized, I think, properly. Yeah, this is definitely something wrong with it. So it doesn't seem to work when the, but I think this actually got to do with the initialization, maybe. We'll see. Okay, but that's for the next. That's for next video. So I should actually write it down here what I'm doing next video. So fix these, make sure simplify works, and then next to do add support more than 2 qubits, summarize bugs. Yeah, awesome. I really hope to be able to make more videos. I'm I'm really doing my best here, but time is a scarce resource recently. Anyway, awesome stuff. At least we got 2 new functions implemented.